Hey guys, welcome back to another round of chemistry notes. In this video, we are going to look at those chemical equations we learned in the last video. We're going to look at them a little bit more in depth and start seeing where they come from, why they look the way that they look. So before we can jump straight into that, we need to practice a little bit counting atoms and ions as they are given to us, because that's a skill we're going to need really for the rest of the year. What we're given here, these formulas, are things you might see in a chemical equation. They're kind of pieces of a chemical equation. A lot of times you'll have a coefficient out front. This big number out front is the coefficient. So here that is a 2. And that distributes to everything that comes after it. So if we were going to talk about the number of ammonium ions here, the number of NH4 ions, that's a new ion as of this 6 weeks. You should memorize that one. Ammonium, NH4 plus, know it, love it. In just one, if this 2 weren't here, in just one of this formula, there are 2 ammonium ions because we've got our ammonium with a little 2. But this 2 is here, so we have 2 times 2 is 4 ammonium ions in this section. And we've got this sulfide ion. There's no subscript after it, so that means that there's just 1. If this 2 weren't here, there would just be 1, but the 2 is here, so there are 1 times 2 is 2 sulfide ions. So that's if we wanted to break this up into ions. If we wanted to break it down a little bit farther and count by elements, we could do that as well. Might be a little easier to do it from here. If we have 4 ammonium ions, each ammonium ion has 1 nitrogen and 4 hydrogens. So here we are looking at 4 nitrogen atoms. So we've got 4 ammoniums, each one has 1 nitrogen. We have 4 times 4 is 16 hydrogen atoms, and we have 2 sulfur atoms. We could get the exact same numbers from here as well. We have 2 times 2 ammonium atoms, and each one has this 1 nitrogen. We have 2 times 4 times 2 is 16, and 2 times 1 is 2. The reason we're doing this at counting as ions and counting as elements is we're going to learn how to balance these equations here in a little bit. We're going to make sure that we are starting and ending with the exact same number of atoms. If we start this reaction with 4 nitrogens and 16 hydrogens and 2 sulfurs, we better end this reaction with 4 nitrogens and 16 hydrogens and 2 sulfurs. So sometimes while we're doing this, it'll be easier to work by individual element. Sometimes it'll be easier to work by ion. It's just going to depend problem to problem, so we're going to practice both ways. All right, looking at our next row, there's no number out front. If you don't see a number out front, the implication is that it is a 1. So you can write a 1 there. 1 magnesium hydroxide is not wrong. It's just a little extra work. So breaking this down, we've got magnesium and we've got hydroxide are the 2 ions. Magnesium does not have a subscript, which means there is 1 magnesium. If you don't see a number, the implication is that it's a 1. So we have 1 magnesium, then we have hydroxide with a 2 as a subscript, so we have 2 hydroxides. If we wanted to break this down by element, we have 1 magnesium, and this 2 distributes in 2 oxygens and 2 hydrogens. Again, these mean the exact same thing. The atoms you see in this box should be the same as the atoms you see in this box, should be the atoms you see in this box, because they're all the exact same thing. All right, looking at our next one, this number out front, that coefficient is a 2, which means it's going to distribute to everything that comes after it. So we've got a calcium right here, and we have CO3. Remember, CO, that's not a thing that we know. So this 3 is part of it. This is the CO3, the carbonate ion. So in just one of these units, we've got 1 calcium and 1 carbonate. But there are 2 of these units. So we have 2 calciums and 2 carbonates. The 2 distributes to here, and it distributes to here. Breaking that down into individual elements, that obviously means we have 2 calciums. This 2 distributes to carbons, so we have 2 carbons. And the 2 times 3 means we have 6 oxygens. All right, take a second, see if you can work through the next 2 rows on your own, and pause the video while you're working, and then unpause when you're ready to check it. All right, so for our next one, the coefficient out front is a 3, so that distributes to the aluminum and to the cyanide we are looking at, which gives us 3 aluminum ions, and 3 times 3 is 9 cyanide ions. Breaking that down to individual elements, we obviously have 3 aluminums, 9 carbons, and 9 nitrogens. Hopefully that's what you got. If it's not, go back and see what happened. And then take another look at the last row, see if you want to change anything before you check your answers. Here we go. On your last row, the coefficient out front, that's a 2. So then we have 2 times 3 is 6 beryllium atoms, and 2 times 2 is 4 phosphate ions. 6 beryllium ions, 4 phosphate ions. Breaking it down to individual elements, we have 6 berylliums. We have 3 times 2 is 6. What did I do? We have 2 times 2 is 4 phosphorus atoms. And we have 2 times 2 times 4 is 16 oxygen atoms in our last one. All right, hopefully you are now feeling comfortable with the skill of counting ions and counting elements, because we're going to go ahead and apply that to the new skill of balancing chemical equations. The goal in balancing chemical equations is to make sure that we have the same number of each element on both sides of the arrow. You should have the same number of atoms in your reactants as you have in your products. That is the law of conservation. That is the law of conservation of mass, and we have to obey the law. All right, so here are your steps. I'm going to give you steps. You will probably eventually stop even thinking about the steps, but for right now, they'll probably be helpful. Step 1, if you are given a word equation, translate it to the chemical formulas. That's a skill we've learned. It might be a little rusty. Go ahead and dust that off. You're still going to need it. As you're doing this, remember your naming rules. If it's covalent, if it's 2 nonmetals, it's going to be using prefixes. If it is ionic, if it's a metal and a nonmetal, or if it's made of polyatomic ions, you're going to need to look at the charges, make them cancel. How many of your positives, how many of your negatives do you need? And don't forget your diatomic elements. That is your Brinkelhoff. These elements exist in pairs. You're not going to be told that. You just have to remember. All right, so that's all step 1, is take the words you've been given and turn them into formulas. That's old. That's not a new thing. Here is a new thing. You need to balance one element at a time using coefficients, using the big numbers out front. Do not, under any circumstances, change the subscripts. Don't change the little numbers. That is changing the compound. That is breaking the rules. Don't break the rules. We're going to change the coefficients out front. You'll change one element at a time, making sure they are balanced. Balanced meaning same number on the left side, the reactants, and the right side, the products. Balance all your elements through, and when you're done, make sure that your coefficients are in the lowest whole number ratio. If you can divide them all by 2, divide them by 2. They should not have a common factor. A couple of tips before we get into this. First, polyatomic ions can be treated as a single unit, but only if they stay together. So that's why we practice counting ions. There are some specific reactions where the polyatomic ions stay as polyatomic ions. They rearrange, but if you start with phosphate, you end with phosphate. And in those cases, it's really easier to count phosphate. You can do that. If an element is found in multiple places on one side of the arrow, you're going to balance that element first. Just get that one out of the way. You might have to go back and change it, but at least you'll have made an attempt. And last but not least, you're going to want to balance carbon, hydrogen, and oxygen in that order. This is more important sometimes than others. We'll see some examples, but just keep this in your brain. Carbon, and then hydrogen, and then oxygen. All right, so let's see some examples here. In this case, we are given the formulas, so we don't need to try and write them out. We have aluminum hydroxide reacts with, this is sulfuric acid, to produce aluminum sulfate and water. And you can see we have aluminum. To start with, we have aluminum in the hydroxide ion, hydrogen in the sulfate ion. Ending, we have aluminum and the sulfate ion. And then water can actually be written. H2O means two H's, one O. We can write this as H and then OH. So wouldn't you know it, we've got hydroxide and hydrogen. So we've got our polyatomic ions staying together on the left side and the right side. If that does not make sense to you, if you're looking at this and saying, I see water, I don't see hydroxide, that's fine. You don't have to do it this way. It's just, well, it's definitely easier to do it this way, but you don't have to. Ooh. The following steps will apply to you regardless. So here we go. To balance, a good first step is to just write out the things you have to balance. So over here we've got aluminum, we've got hydroxide, we've got hydrogen, and we have sulfate. And then even though they show up in a different order over here, we're going to list them in the same order as we had on the left. So aluminum, and then we have our hydroxide over here, then we have our hydrogen, then we have our SO4. Once we know what we are balancing, we need to figure out how many of each thing we currently have. So this is where we're going to practice counting atoms, counting ions. Currently, these blanks are empty, which means we can assume the coefficient is 1. So here in AlOH3, we have 1 aluminum and 3 hydroxides. Here in H2SO4, I can show this a little bit more clearly, we have 2 hydrogens and 1 sulfate. Over on the right-hand side, we've got 2 aluminums over here. We have 1 hydroxide over here. We have 1 hydrogen. And we have 3 sulfates. So this is where we're starting. Sometimes it's already balanced the way it's given to you, but this is not one of those times. We start with 1 aluminum and we've created a new one to end up with 2. We started with 3 hydroxides and we've destroyed 2 of them to end up with 1. We destroyed a hydrogen and we created 2 sulfates. This is madness. This is not balanced. So we're going to go ahead and start. And as you start working more and more of these problems, you may come up with a pattern that works for you. I'm just going to start at the top. Aluminum, we have 1 and we have 2. That's not balanced, so we need to balance it. We need more aluminums over here. If I put a 2 in this blank, if I create a coefficient of 2, notice I did not put a 2 down here. Please do not try to balance with subscripts. That's no good. But if I put a 2 in this blank, now I have 2 aluminums because it distributes to this aluminum. but it also distributes to this hydroxide. And now I have 2 times 3 is 6 hydroxides. So by putting this 2 here, I fixed aluminum, and now hydroxide is real screwed up. So we can go ahead and fix that one now. We don't have enough hydroxide over here. We need more, so we can put a 6 here. And this 6 will distribute to this hydrogen, and it'll distribute to this hydroxide. So now I have 6 hydroxides, and I have 6 hydrogens. However, I only have 2 hydrogens to start with. I need to start with 6. So if I put a 3 over here, then I'll have 3 times 2 is 6 hydrogens. That 3 distributes here. It also distributes to our sulfate. So now we have 3 sulfates. So now we've got 2 aluminums, 6 hydroxide, 6 hydrogen, 3 sulfate, 2, 6, 6, and 3. And that's why I recommend you do them in the same order, so it's really easy to tell. 2, 6, 6, 3. This is balanced. We're done. You can leave this blank. You can also write a 1 into it. Either way is correct. And we don't have a common factor that we can divide any of these by, so we don't need to worry about that. Cleaning this up a little bit so it's a little easier to read, our final answer is when 2 aluminum hydroxide react with 3 sulfuric acid, it produces 1, and I'm actually not going to write the 1, it produces 1 aluminum sulfate and 6 HOH. This is a perfectly okay way to write this. Probably slightly better is to write it as 6H2O. And that's our final answer. That's our balanced equation. A little weird. I promise it gets better every time you do it. So let's look at another one. Our second example here, we have when solid iron is combined with oxygen gas, the solid compound iron 3 oxide is produced. Notice we're given the words, which means we have to write the formulas. Some of these are easy. Solid iron is just elemental iron. It's just Fe. And we're told it's solid, so we should put that. Is combined with oxygen gas. Again, that's just elemental oxygen. So it's oxygen that is a gas. Hopefully this looks really, really wrong to you because oxygen is one of your diatomic elements. It should never look like this. If it's just oxygen by itself, there need to be 2 of them. So this is oxygen gas. And then the solid compound, iron 3 oxide, is produced. So remember, this is ionic. This iron 3 tells us it is an iron ion with a 3+ charge. And oxide comes from oxygen. If you look on your periodic table, oxygen forms a 2- charge. So that means that when they come together to form an ionic compound, we are going to need 2 irons and 3 oxygens, and that'll be a solid. Let's go ahead and write our initial unbalanced equation. We have solid iron reacting with, leave a space for a coefficient, oxygen gas to produce, leave a space for a coefficient, iron 3 oxide. That is a solid. So again, this may already be balanced, but we should not assume that. So we need to write out that we have Fe O, we have Fe, we have O. Here on the left side, we have 1 iron and 2 oxygens. Here on the right side, we have 2 irons and 3 oxygens. Neither of these is balanced. So we can start wherever we want to. I will tell you that when you have just one single element all by itself like this, that's going to be sort of the way to fix that's a really good thing to leave for last. So we're going to save iron for last, or I am, you do you. And I'm going to look at oxygen first. So here I've got 2 oxygens on this side, and I've got 3 oxygens on this side. Well, there's nothing I can just put here to make it 3, because they have to be whole numbers. There's nothing I can just put here to make it 2, because again, they just have to be whole numbers. But if I put a 3 here and a 2 here, then I'll have 3 times 2 is 6, and I'll have 2 times 3 is 6. So now I've got my oxygen sorted. And I have, by adding this 2 here, I've said I have 2 times 2 is 4 irons. So then if I put a 4 out front here, that'll give me 4 irons. Now both sides has 4 irons, 6 oxygens. All is right with the world. That is my balanced equation. I can put a box around that and call it a day. You have probably witnessed this equation, this reaction described in this problem. It's not a very fast reaction, but if you've ever gone to pick up something metal and your hand comes away orange because it's covered in rust, that is the result of this reaction. You put out something that is iron or even steel. You put out something that is iron, it reacts with the oxygen in the air, and as a result, you get iron 3 oxide, you get rust. So, fun facts. All right, next you have quite a few practice problems. Go ahead and pause the video, work through your practice problems. Some of them require you to write formulas, some of them give you the formulas. When you're ready to check those answers, unpause the video to see how you did. All right, these are what your next 7 problems should look like. Again, in some places the 1 is written, here the 1 is written, here the 1 is not written. Without the 1 is sort of more normal, but if you want to put that 1 in there, you are welcome to do it. If you would like a little bit more in-depth explanation of this, the keys are up on my website and you can go see how I got to these answers. But if you're doing good, there's just one more thing we need to talk about in this video. So go ahead and keep on moving. We'll talk about one last thing. Those are ratios. The coefficients, those numbers out front in a balanced chemical equation, can be used as ratios of substances. That's one reason that we balance. First, we balance so that we are obeying the law of conservation of mass. But also, once the equation is balanced, it's a very, very useful tool for us because those ratios can describe individual molecules, or they can describe everybody's favorite, the mole. And we can express these as fractions. Do you see where it's going? Have you figured it out yet? So for example, we have 2H2 plus O2 produce 2H2O. What we can glean from this is that for every, remember, if you don't see a coefficient, the coefficient is a 1. So for every 1 molecule of O2 that is used, we are going to produce 2 molecules of water. Or for every 2 molecules of H2 that are used, 2 molecules of water are formed. Or for every 1 molecule of oxygen that reacts, 2 molecules of H2 also react. Or for every 1 mole of O2 that reacts, 2 moles of H2 also react. So regardless of whether you're talking about molecules or moles, and we've talked about this a lot this year, the ratio remains the same. Whether it's 1 molecule of O2 reacting with 2 molecules of H2, or 1 mole of O2 reacting with 2 moles of H2, this reaction is always going to be the same. And since this ratio is always going to be the same, we can use it as a conversion factor for dimensional analysis. We could write this just as easily as for every, looking at letter A, for every 1 molecule of O2, there are 2 molecules of H2O formed. Or we could say for every 2 molecules of H2, there are 2 molecules of H2O formed. Any of these sentences can be turned into conversion factors. We're really not going to use these all too often. We're not going to just discuss the sentence very often, but we are going to use these a whole lot. So we're going to do one more practice together, then y'all will have some time to practice balancing and coming up with conversion factors. So here we go. Example number 2 here says aqueous hydrogen nitrite decomposes to produce aqueous dinitrogen trioxide and liquid water. Oh boy. So we'll start with this aqueous. Again, it's just going to tell us that this thing is, the symbol is AQ. Hydrogen nitrite. So as you should know, as of this 6 weeks, hydrogen can actually form an ion, H+. And nitrite, you should have memorized, is NO2-. So hydrogen nitrite is going to be HNO2. We need 1 hydrogen and 1 nitrite to make their charges cancel. So that's going to be our only reactant because then that's going to decompose. So we start with HNO2 aqueous, decomposes to produce aqueous, again, just that AQ, dinitrogen trioxide. That's just a covalent compound. It's telling us what the formula is. Di means 2, nitrogen means nitrogen. So leaving a space for a coefficient, we have N2. And then tri means 3, oxide means oxygen, so we have O3. And again, that is aqueous. And liquid water. Again, if you are told the states of matter, write the states of matter. So now we need to balance this. We've got ions over here on the left. We've got a nitrite ion, but it is nowhere to be seen on the right. So that keep your ions together shortcut is not going to fly here. We're going to have to do this one element at a time. So we've got hydrogen and nitrogen and oxygen. Then over here we have hydrogen, nitrogen, and oxygen. In our reactants, we have 1 hydrogen, we have 1 nitrogen, we have 2 oxygens. In our products, we have 2 hydrogens, we have 2 nitrogens, and we have 3 plus 1 is 4 oxygens. Don't forget to look out for elements showing up in more than one place. We said that if they do that, we should probably balance those first. So let's go ahead and do that. We've got more oxygens in our products. We've got 4 oxygens. We only have 2 oxygens in the reactants. So if we put a 2 out here, then we'll have 2 times 2 is 4 oxygens. But that's also going to change to 2 hydrogens and 2 nitrogens. Then over here, we've still got 2, 2, and 4, 2, 2, and 4. This is balanced. So now that we've got our balanced equation, we can get rid of some of the scratch work, give ourselves a little bit of room to write some conversion factors, to write some fractions. Again, there are plenty of different ways we could do this. We could do 2 moles of HNO2 over 1 mole of N2O3. Or we could say that we could flip it and change the units. For every 1 molecule of N2O3, we use 2 molecules of HNO2. Or we could have flipped it without changing the units. We could have said for every 1 mole of N2O3, we used 2 moles of HNO2. We've been ignoring water. We could say that for every 1 molecule of water that we produce, we also produce 1 molecule of N2O3. There are so many different ways you could do this. We obviously are not going to write them all out. Maybe you wrote down something different. That's great. You just need to practice identifying that once you've got a balanced equation, you can use these coefficients to describe amounts in moles, amounts in molecules, and to relate them to each other. All right, so now you've got some practice in your book. Different kinds. Some of them have you writing equations and then balancing them and then coming up with conversion factors. Some give you the equation, you just have to balance it and come up with the conversion factor. Lots of different things to play with here. So go ahead and pause the video, take a couple of minutes, work through these. When you're ready to check your answers, unpause the video. All right, hopefully this is what you ended up with on those practice problems. For letter D, again here, these were just the first 3 that I thought of. You may have thought of 3 completely different conversion factors. You may have flipped yours on your head from mine. You may have used molecules where I used moles and vice versa. That's fine. As long as you are using the coefficient with the correct species, with the correct formula, that's fine. You're doing good. All right, so hopefully this went well for you. If not, maybe go back through the video, go back through your notes and try it again, or as always, come into tutorials. But this is it on the notes for balancing equations. Moving forward, this isn't a lesson, it's a skill you'll have to use. So make sure you're getting lots of practice, getting comfortable.